It's easier to give that talk after sort of Armando set the context. What I want to talk about is not the cloud per se, but sort of the machinery that actually powers it. At Google, I think I was lucky enough to actually work both as a software and a hardware engineer. And what I want to give you is a brief description of what the machinery looks like, but also focus most of the time on some of the issues Armando raised, and that these warehouse scale engineers have to actually sort of make these problems of scale go away. I want to give you a glimpse of the complexity of these problems and how fascinating they are for us at Google trying to work on them. So this is how a hardware engineer today, I think, sort of sees the world, at least sort of from my standpoint, in the context of a cloud. The universe in this space is shifting to the edges of the space, right? There's a lot of interest in portable devices and things that don't do a tremendous amount of computing. Their main role is to interact with you, be very good, your iPhone, your super portable laptop or something like this, and whatever heck comes up in the future. Then there's really good internet sort of going on somewhere that sort of enables this whole thing to happen, of course. And then services that are provided to you not by software running on your PC, but on services that are running on these really large facilities that we call warehouse scale computers. This is trying to give you a more physical view of what we mean by warehouse scale computing. In this case, what we have back there is the Columbia River. This is a facility we have in the Dalles in Oregon. And what you see there is the reason why we call this warehouse scale computing. These things look like two very large warehouses. And inside them, there's sort of lots of machinery. Now, we make a point of calling that a computer, that's singular, as opposed to sort of a cluster of computers, because that really permeates the way we build and the way we program these things. Our workloads don't run on one server. They don't run on 100 servers. A lot of the workloads that we are interested in run on things that are the size of these warehouses. So we can't think of individual computers when we're programming to this. We have to think of this whole infrastructure as one very large computer. One way to help you sort of think, help you believe my analogy, is to just look at these warehouses as being, two big CPUs sitting on sockets on the motherboard, right? And of course, CPUs generate heat, and you have to remove that heat. And for that, instead of heat sinks and fans, we have these 30, 40 feet tall cooling towers sitting on the back of these facilities over there. And then finally, you have to provision these things with power. Instead of voltage regulators or power supplies, we have actually a whole electrical substation that you can barely see that on the right-hand side that had to be built so that we could actually power that facility. So, things are big. Now, the reason why this thing is so successful is that for many compelling applications, these machines are just much better than lots of PCs. The typical example for this is web search. I guess this is one way to sort of get the math right. If you have millions of users with millions of PCs, don't do nearly as good a job on some applications as a few thousand servers can do. And search is the canonical example for that. And you probably have a mental model of what that is, but it's interesting to just think about how much computing is behind every one of your Google searches. Especially today when you're not just searching the web. When you send a search our way, we have this thing called universal search that actually searches just about every document we know, right? Images, news, blogs, video, etc. Right? So the amount of computing behind this is just tremendous, and it's beyond the capabilities of what you think would be feasible, especially in the sort of fraction of a second that you like your search query to be responded to, if we're using sort of just a regular PC for this. So very compelling for these large applications. Another sort of typical application that's sort of flagship for these types of systems is language translation. I don't know about you, but I'm pretty impressed of how good machine translation is these days. I mean, the products that the folks at Google have put to it are quite interesting. My wife is beginning to learn Portuguese, and she gets email from my family as well every once in a while. And Google Translate actually does work for her. Most of the time, they get things right. It's another example where these language models, especially for statistical machine translation, require just a tremendous amount of data for training for them to be effective at all. And then you have to do the lookups on the fly in a way that translation is interactive for you. And without sort of having that system running on this consolidated computing farms, it's very difficult to imagine provisioning this to the world at reasonable prices. So this is just to illustrate how efficient this is. And in this case, it's just an example we did about a year and a half ago when there was some press that was sort of grossly overestimating what the carbon footprint of Google was. So we did sort of, slightly better than the back of the envelope calculations, and we look at it, it's actually pretty darn good, right? If you think about it, your weekly laundry workload sort of has probably a larger carbon footprint than your yearly Google searches. So that sort of illustrates or drives home how efficient this model can be for these applications. So what I wanted to do today is to just briefly walk you through the machinery and then focus most of the time on what it takes to make that machinery useful for you. And that is, challenges from a programming standpoint of dealing with things that come off out of the just huge scale of these machines. A lot of it will be dealt in more detail by YY and Partha a little bit later, so I'll try to be brief on those. The first part of it is basically focusing on what makes programming complicated. And the second, giving you a glimpse for why energy efficiency is just important in that context at a fairly high level. So this is the schematic slide for what the machinery looks like. So you have lots of servers. A lot of them look like these 1U servers. The IBM will sell you many good ones of those. They're stacked together in racks. These racks have some kind of switching gear, either on top of the rack or somewhere in the middle. You can see that blue sort of line on that rack. The numbers vary, but that's sort of the right order of magnitude. And then somehow you wire these rack together in big data center level switching fabrics, and you can get these things to be extremely large. I mean, the data centers and clusters, they're well over 10,000 machines sort of out there. We certainly have lots of them. So to give you not the schematic look, but some more of a, well, actually, the thing that I want to highlight is that the programming complexity, of course, goes up quite a bit on scale in multiple dimensions. I'll give you just a taste for it on the upcoming slides. Before I do that, I hope that the dimness of the video doesn't sort of detract too much. I wanted to actually give you more than just a schematic look, but a very glimpse view of physically what that looks like. About a year ago, we disclosed the fact that back in 2005, our team built the first fully container-based data center. So this is a data center for which the machines were housed not in rooms, but as Armando alluded to earlier, inside 40-foot shipping containers. And the data center was put together out of a bunch of these. In this case, the room I'm going to show you has, I think, about 44 shipping containers, each one of them with just over 1,000 machines or so. And that sort of makes up the machinery part of the data center. I'll walk you very briefly through it. So these are two floors of about, in this case, 10 or 12 containers stacked up together, so they're on the side. The machines are inside it. A brief look at the cooling plant. Red pipes are hot water. Blue pipes are cold water. The rest of the cooling plant is outside the building. These are the cooling towers that actually expel the heat to the environment. You see now inside the data center, each of these doors is towards one of these shipping containers. This technician is looking at some server he's actually repairing. Those doors are into the containers that you see right now with computing equipment on both sides and a little bit of graffiti at the end. They don't look very pretty. Lots of blinking lights. This technician is removing sort of a dummy that's preventing airflow from going through an empty slot and actually putting together a server he just repaired and leaving. It's a little bit noisy, but otherwise not that unfriendly an environment. And of course, after he leaves, the lights go out. And that's, with a little bit better lighting, you'd see, it's actually a pretty picture of the data center at night with lots of just blinking lights. Now, so that gives you sort of an idea of what, the containers are not the only way to design very efficient data centers, but it was sort of a clever way that sort of we did it sort of back then. And certainly has some advantage in terms of speed of deployment for some kind of situations. What I wanted to focus on right now is that how do you make this massive computing infrastructure actually usable for programs that are also massive? And I'll start with giving you an idea of how just the complexity of the storage hierarchy affects that programming challenge. What we have here is just a sketch of how much DRAM is available to you as a program running on one CPU of this warehouse scale computer can see, right? Locally in your own machine, you may have 10 or 16 gigabytes of memory, so it's locally accessed into that machine. The DRAM is directly connected to your CPU. Now, if you're able to actually use the DRAM that's connected to other machines in your own rack, then you have close to a terabyte of DRAM potentially sort of available to you. That's sort of much better. And then finally, for the entire data center, in this case, I think I have an example that has sort of about 10,000 servers or so. you get close to the petabyte range of DRAM that's available, and it's also very good. Right? Now, that comes with idiosyncrasies. The most one is that the performance that this comes about. So let's assume that your program needs to read a megabyte of data. If you're lucky enough that that data happened to be in your local machines, no problem, right? There's a couple of hundred microseconds or so, and you can get that done. If otherwise the data set is too large and doesn't fit in your own machine, you have to go remotely. Well, within your rack, then you're sort of more close to the 10 millisecond range to access much more data. And then finally, if you're all the way to the data center, because of the fact that the bandwidth across racks is not nearly as good as the bandwidth within one of these racks, then your time to access that data sort of goes up by nearly a factor of 10 as well. So you have a lot of storage available to you, but you have to be extremely careful about how to place them and how to manage them, because your performance can fall off one of these cliffs very quickly. And notice that I've only talked about DRAM here. Of course, there's things like disk drives, right, which are, 100,000 times slower than DRAM, but dirt cheap. And then there's something in the middle these days, which is these flash devices that are still pretty much 1,000 times slower than DRAM at also a performance cost. So you have this array of cost of devices with different cost performances, and then spread out in this data center in different ways. That gives you a very complicated storage hierarchy. You don't want to expose a productive user or a productive programmer to the complexity of that hierarchy. And so that's the kind of complexity that the people who are building the infrastructure software for these machines to provide cloud services have to try to somehow hide from you. Now, the other thing that's interesting about large scale, that's sort of obvious, but I think it's important to point out, is that your exposure to rare performance idiosyncrasies grows in a very unfortunate way, right? So assume, for example, a situation where you have a program that you work very hard on. It's a web server of some kind. And that, it gives a very fast response time most of the time, sort of 100 milliseconds or so on the average. But every once in a while, because, something is happening in the background consuming some of the CPU, that may take, as much as, a second or so. But it's rare, sort of 1 out of every 10,000 requests or so. Now, if you have a system that's using one machine, that's actually not too bad, right? 0.1% of your requests will have some kind of performance impact. Now, if we are sort of at the warehouse scale, then statistics are not your friend, right? If indeed your system relies on robust performance out of all of these machines, then you're in deep trouble, even with the performance hiccup that seems to be completely irrelevant in a single machine. So it's a very difficult problem to solve, because you can't completely make that 0.1% be zero, right? All you do is hammer that thing down. So the designer of these facilities tries to make that as low as possible. And then the programmers have to work on hiding these performance idiosyncrasies the same way that programmers try to hide faults, for example, in some situations. This is something that's as bad as a fault, and in some cases indistinguishable from a fault scenario. Speaking of faults, of course, there's lots of ways of thinking about the exposure to faults in these kinds of services. First, you have to remind yourself that you're only as reliable as the quality of your pipe to your user, right? And unfortunately, or maybe fortunately in many cases, you have the internet between you and your users as a cloud provider. And the internet is not that available, right? And there's lots of studies out there that give you estimates for this. But depending on your luck between the two endpoints that you choose to connect through the internet, your connectivity may not actually get to 2 nines, right? So that's something you have to keep in mind. And then, of course, within your facilities, this is sort of what the hardware landscape looks like, right? 1% of your machines will probably see an unrecoverable DRAM error, something that your ECC codes can cover, and you have to sort of deal with that. Disks are particularly flaky. We published a study about this in 2007 at a fast storage conference that gives you more details about what goes on there. But you can expect that between 2 and 10% of your disk drives will actually fail within a year, are going to have to be replaced. Which is a fairly high rate and a very large number if you had too many disk drives to begin with. And then finally, even very robust system software and operating systems will actually have crashes, sometimes because of software, sometimes because of idiosyncrasies of the hardware itself. So you can expect an order of a couple of crashes. That means sort of unplanned crashes per year for every server that you have. And not to mention, in some parts of the country in particular, especially during the summer, power tends to be somewhat unstable. So as a facility, you have to be able to survive a certain number of utility outages per year smoothly, right? And that depends on the quality of your backup solutions and generators and things like that, and you have to be ready for that. Now, a couple of things to think about, again, is to bring scale back, right? If you have just these unplanned 2 crashes per year, if your cluster has 2,000 machines, you can expect something on the order of 10 machines crashing per day. So a crash is not an unusual event. A crash is just what happens on Monday and on Tuesday, right? So you can never provision your systems and actually benchmark them assuming fault-free scenarios. You're not only always having to deal with fault, as well as deal with the resources that are necessary to recover from failures constantly. Finally, we haven't talked about planned events, right? Planned events are extremely important because we are in a world that is very dynamic. We want to innovate as fast as possible. That means we want to upgrade software as quickly as possible. And that means outages as well. And in our case, these kinds of outages actually can dwarf all the unplanned ones. And then finally, there are service level outages that are very affecting sort of an entire facility as a whole, right? And these tend to be very serious networking issues. Things like power events that you didn't recover for some reason, a malfunctioning generator backup, for example. And then, of course, operator errors. There's a myriad of examples of why long-haul connectivity is not just expensive, as Armando pointed out, but actually extremely flaky. I can talk to you about some of these anecdotes, and it's fantastic. The different kinds of ways you can lose connectivity to large parts of the world. I don't think I have time for it today, but I'll use that as a teaser for conversations later on. I want to close out talking about energy efficiency because it's something that's so much associated with data center facilities that I think we have to touch up upon. Partha is going to go to think a little bit more detail on this. I want to give you just a very big picture and some of the challenges we look at. First, is electricity the main source of a cost, if you will, for large-scale data centers, right? And the popular press seems to indicate that that's true, but the message is a bit more nuanced than that. Electricity, if you actually provision systems correctly, and you consider just the cost of machinery, computing machinery, of building the data center itself and providing and provisioning electricity, it's definitely not a dominant cost. Right? So why is it that people care about energy efficiency in this regard? The reason is that the cost of the facility itself, there in blue, is an energy-related cost. It just happens to be sort of a fixed cost, if you will. But data centers are not priced by the square footage as they were in the 80s or 90s. They're priced by the watt. So if you need a facility that's going to have to deliver 20 megawatts as opposed to 10 megawatts, that facility is twice as expensive. If you need a facility that's twice as large in terms of footprint, it will not be twice as expensive. So the real way to account for energy-related costs is sort of all of that piece of the pie. And as you can see, that begins to be really interesting. Right? So you definitely have to worry about that. So what are we doing about this? Very briefly, I'll point out sort of 3 different areas that we focus on. One of them is just, getting great data center designers and engineers from the mechanical and power distribution areas to just make that part of the system work very, very efficiently. That means the losses involved in in distributing power throughout the data center, as well as removing heat from that facility, have to be very small. There's this issue of energy proportionality. That's something that we hammer on quite a bit. I'll go over it very briefly as well. And then, of course, there's the way we write software that affects this in a way that it's kind of obvious that people tend to forget. Talking about data center level overheads, right? What the facility does for you. This is a picture of what at least in 2008, where the watts were going in a typical data center facility, according to this study. Out of every watt that enters the building, only 50% of it is actually powering any computing equipment at all. The rest of it's divided, actually most of it, in the mechanical or cooling infrastructures, that's at 35%. Some significant amount are due to losses in transformation and rectifying inverters and things like that. And then miscellaneous sort of losses, that little 4%. So in the end, you're actually paying, if you will, twice as much and building twice as large a facility as you might have needed in terms of heating and cooling. So there's lots of interesting things that we've done at Google to actually bring those down to a point that overhead that used to be a factor of 2, like 100%, came down to sort of 16% or so. And I can tell you more about this. There's a lot on the web. If you just search Google for efficient data centers, there's this entire data center summit where I actually go through and explain what we actually did to achieve these very, very high efficiencies. What happens then is that now we have to worry about the 86%. How do you make computing equipment very energy efficient, which is something that perhaps you could afford to ignore when they were perhaps a smaller fraction of the overall power consumption scheme. So one observation we have, and this is one of the many issues that relate to energy efficiency, and the one that I think is particularly obvious in the data center environment, is to just observe the mode of operation of these machines. Data centers, when you talk about many thousands of machines, happen to not be running full blast all the time. Right? They are designed to run at a certain maximum speed, but they're provisioned to run at a relatively lower speed because that's the easiest and most robust way to offer these services. You buy a car that can do 140 miles per hour, you probably don't drive it at 140 miles per hour sort of 100% of the time. So when you look, and this is data that comes from actually 5,000 Google servers over a period of 6 months, and we're plotting the aggregate time that they spend at different CPU activity levels. And as you can see, there's this big blob in the middle. Most of their time is actually not close to the 100% utilization. It's actually somewhere between the 20 and 50 percentile. So our computer, our warehouse computer, sort of spends most of this time at that range of utilization spectrum. Unfortunately, when you look at servers today and computing equipment in general, they actually are particularly bad when they're operating at that range of the utilization spectrum. They're pretty good when they're completely idle because you can actually put them in standby and turn them off, and that works very well for your cell phones and your laptops. They're actually not bad at all when they're running full blast because that's where they're benchmarked, right? But where they actually used, which is in sort of that middle range somewhere, you're actually in trouble. One way to think about energy efficiency is to divide that x-axis by the y-axis, right? And what that gives you is a curve that looks like that green one over there, which is your energy efficiency curve. And it's a sad story, right? Because it peaks only when you're at 100%. If you're not running at peak, you're actually at a much lower energy efficiency than your benchmark would tell you were. And in particular, as you can see, when you approach the 20 percentile and 10 percentile, it just disappears, right? You're close to sort of half of your peak energy efficiency when you're actually running that machine where it's supposed to be running to begin with. So what we'd like it to have is for that green curve to be totally horizontal, right? That means efficiency is flat across the utilization spectrum. And we call that energy proportional systems. It's a kind of a clumsy name for something that's fairly obvious. What if we could build machines that work like that? That if they did no work for us, they don't consume any power. They did a lot of work, they consumed a lot of power. But in particular, if they actually did 10% of their maximum amount of work, they consumed 10% of their peak power. Seems reasonable, right? Computing equipment hasn't been designed in general to work that way, and we're trying to change that, trying to make that happen. And one of the reasons we want to make that happen is that we've studied that issue in detail at Google, and we see an enormous opportunity for energy savings. In this particular study on the Computer Architecture Conference a couple of years ago, 3 years ago, we extrapolated that if all our machines had the kind of energy proportionality properties that we like to have, we would be, halving our energy consumption, which is quite substantial. To inspire people working in this area, I like to give them an existence proof of a machine that is energy proportional, and that's the adult male. I got this from a physiology book, and it's interesting to see the kinds of categories that they choose. But if you think about it, humans are fairly energy proportional, right? When you are sleeping, you don't consume an awful lot of energy. And if you are axe chopping, I guess, you consume a lot of it. I have no idea why they pick these things. But they're fascinating. I especially being Brazilian, like the lambada over there, somewhere in the middle. Anyway, it should be possible for machines to be designed that way. We know one that works sort of like that. So finally, we can actually make software make a difference for energy efficiency. And people sort of forget about this. One of them is sort of what I call the hard way. If you have machines that are only energy efficient when they are completely powered off, you have to design software systems that are actually fairly complex. They have to go around and then figure out when you actually don't need as much computing as you might need at peak, move all that computation, in particular that data somewhere else, and then power everything off, and then be very smart to power everything back very quickly when you need that. And it does work, but it's very, very hard to do. And for the majority of interesting applications, we actually don't see that working very well. And I can go to a little bit more detail with you why this is, in practice, fairly different for interesting applications. Now, there's something else that's actually fairly easy to do that's guaranteed to give you energy efficiency, which is actually to write fast software. I looked around, and I find very, very few examples of situations where software optimization makes a system less energy efficient, right? So, and just to give you one example, one of them that may do that is, aggressive speculation. If you have systems that try to, gain 10% of performance by redundantly computing the same thing in 8 different machines, that might actually not be a win in terms of energy efficiency, even if it may be a win in performance. But aside from that, there's very, very few examples of tricks that software engineers do to make systems more efficient that will actually make the overall system more energy inefficient. So that's the good news. To close out, I hope I was able to point out to you some of the challenges of actually making that machinery be a useful computing infrastructure for cloud scale applications. Many of the issues that we have today are a side effect of scale. They come about because it makes the storage infrastructure much more complex. They make performance or small performance issues be of a much greater scale. And of course, it makes the dealing with failure something that you can't avoid thinking about. And then finally, energy efficiency is a fascinating topic because it's one that's truly multidisciplinary. So it's a particularly interesting one for a conference such as this one. We have lots of very bright people at Google that are mechanical engineers and power and thermal engineers as well. And all the way down to software engineers talking to each other, trying to solve some of these problems. So it's a great area for interdisciplinary research. And that's all I have for today. And if we have time, I'll be glad to answer a few questions. Thank you.
Okay. Klaus Daniel, Oak Ridge National Laboratory. I found it very interesting where you talked about energy efficiency there, and I see your point on essentially trying to run the system at the peak energy efficiency then. But is there any work going on in trying to make moving a bit or calculating a bit, making that process itself more energy efficient?
Oh.
As an example, at Oak Ridge, we're very concerned about that. We are having two of our supercomputers are in the top 3.
Yep.
And we are currently having those cooling towers out there as well and consuming about 20 megawatts of power there. And if we look into the next generation computing, you look at 200 megawatt, where I think 50 megawatt is a city.
Yep.
So it's getting a big problem.
Yeah. Well, where to begin? Lots of people are actually focusing on this problem. I think we're late to the party right now in terms of thinking about it as an energy output problem. Engineers and computer scientists have focused on that problem initially for the things that bit us in the 80s and 90s, which is how can I improve the battery life of my cell phone, right? And then maybe in the early 2000s, how can I make my microprocessor not melt? So it's really sort of temperature management more so than sort of reducing your overall energy consumption. And I think it's only been for the last maybe 5 years or so that as an industry, we focus on actually, reducing your monthly energy output. But there are lots of people working in pieces of that problem. At the circuit level, as you can imagine, there's lots of bright circuit people that do, there's clock gating that is happening in every logical device that you have. That's essentially one way of actually making inactive logic sort of not be a burden on your power. That's one way to look at it. The moving bits part of it is where we're the furthest behind. Networks are probably the worst example of non-energy proportional computing we have out there. I actually did this experiment a while back where I took an Ethernet switch, sort of a typical one you can buy to connect maybe 48 machines or so with a few uplinks. You put them into the wall, you measure its power, and it gives you probably 70% of its peak power output. If you connect every Ethernet link to that, so that there's PHY connectivity, if you will, but there's no traffic running on that switch at all, it's consuming 99% of the energy that it's consuming when it's running at full blast, right? So it's not that these guys are dumb in any way, shape, or form. They certainly haven't focused on energy efficiency. It hasn't been an issue on their radar screen. It is now, and it's beginning to be more of an issue for that. But different places, microprocessors are doing much better than storage and DRAM. Storage and DRAM is doing much better than networking. So that's sort of the way to look at it.
Hi, I'm Jack Lungalan at Penn State University, and this is kind of killing me. So I understand everything from coyotes to drunken hunters, but how on earth does blasphemy cause a service outage?
So there's various examples. I can give you one of them. There was one country in Asia at one point that had objected to some YouTube videos we had. What it decided to do was to essentially hijack the domain name service for YouTube in that country so that it would resolve to one of their servers so that nobody would see YouTube within that country. It actually made a mistake. They didn't do that on purpose, but they actually made that a global sort of DNS request change. And then there was a cascading mistake of the DNS authority that was right above them decided to believe this relatively, a small Asian country. And therefore, suddenly YouTube disappeared as a name for much of the world. That's one of my blasphemy examples. There are a few others. Yeah.
Swami Krishnan from Caltech. So we have a small high-performance computing cluster in our lab. And after a year's time of building it, I wanted to upgrade it. And before I know it, Dell tells me that, oh, those processors are no longer available. I'm seeing your warehouse. How do you recycle the whole warehouse when you need to upgrade, or do you actually go bits and pieces, but then you have incompatibility, heterogeneity, and loss in performance?
Yeah, good question. We actually do a little bit of everything. We reuse it ourselves. Like, for example, there are times where a particular class of systems may not be most appropriate for our most computing-intensive workloads we have, but they're still actually very useful for some of the less intensive ones. So we repurpose them sort of in place to run different applications. We also actually do upgrades sort of in place. I mean, we talked about unplanned or planned outages in the context of upgrading software. We do upgrade hardware, right? We may provision machines to begin with some certain amount of DRAM that's less than their total capacity, and we do upgrade that. And we actually recycle. I think we have an external report about this. Like 99% of all our components, either by sort of reclaiming the materials and recycling them themselves, or by reselling them when they still have significant value to other people. So they're massive operations. They tend to happen at big chunks, maybe not an entire warehouse at a time, but you essentially do all of it. I guess I can give you sort of more details offline, but there's no shortcuts, and we do deal with heterogeneity, right? We do have some of these big warehouses that actually have multiple types of machines. We try to keep that number to the smallest degree because it does increase the complexity of the programming systems on top of them. But we do that as well.
Bernie Myers on IBM. Have you looked at any paradigm shifts? People have been discussing openly, as you probably have seen, things like going to microservers with the idea that instead of the tremendous amount of programming overhead you need to keep some massive processor with 100 threads, busy, take the other extremists, which is drop everything, have a scheduler and a stupid core that can run at 80% capacity, doing one thing, right? And then you dramatically reduce the overhead software. So you might, in concept, and I haven't seen any proof of it yet, get a real paradigm shift in terms of the efficiency for certain limited cases where getting rid of all the virtualization overhead and just running a scheduler could actually save you enough in the overhead sector that you pick it up as benefit in the actual app. I'm just curious, have you guys looked at that? Is that something that's underway?
We do look at that all the time. And it's interesting because the kinds of machines we use today, people used to consider them very, very wimpy machines to begin with. So I guess, one way to answer that is that to some extent we sort of do that. The key is the degree to which you're willing to sacrifice single-threaded performance to get sort of better other sort of side effects and economic advantages. Partha, actually, who's going to talk later, also somebody who should ask about this, has done some very interesting work in this general area. I'll give you sort of one tidbit. Urs Hotzler, who works with us also at Google, has published an article touching on that issue at a special issue that Partha and I co-edited for the IEEE Micro magazine. Just came out this past month. And it talks about the fact that wimpy cores, that people like to talk about that in that way, have a potential to be much more energy efficient in particular, and then cost efficient as well for those reasons. But it comes with significant overheads from a software development standpoint that can't be ignored. And one of them is the fact that Amdahl's law hasn't quite been revoked just yet. But that argument's put in that article very succinctly, and I'm glad to talk to you in a little bit more detail about this. It's a fascinating area.